Guten Abend, ich bin Nate Guerin. Ich spreche mit Ihnen von Deutschland. And I'm actually going to present in English. Just kidding. My name is Nate Guerin. I'm excited to be with you tonight to show you my computer that I've built during this class. As you can see, this is my presentation outline. I'm going to start right away by jumping into a demo of my computer, and then I'll go over my instruction set. We'll take a brief look at the block diagram and assembler, spend a little bit more time on the emulator, and finally I'll conclude with covering my special feature, which was a hardware multiplier based on a Wallace tree, which allows for constant time multiplication. Okay, I'm going to demonstrate my computer now. I have the program already loaded on the FPGA and the memory initialized with my MIF file. And before I start, I just want to point out a couple components about the computer. So first of all, you'll notice that the 4 left 7-segment displays are going to be showing the program counter. The right 4 7-segment displays are going to show the contents of the instruction register. The red LEDs on the left, they're going to show the control lines that are asserted and deasserted during the different states in my main sequencer. And the green LEDs on the right, they show both the current ALU function as well as the state of the sub-finite state machine that I use for the memory subsystem. So the computer is going to start off, it currently has its clock hold asserted and it's in reset mode. It's going to start off with the highest clock divide limit possible, so you can see the computer run at a really slow speed and see all of the control lines turn on and off. I'll slowly speed it up by increasing or decreasing the clock divide limit by a power of 4 until we get to full speed. And without further ado, here we go. So you can see this is already, it's the highest clock divide limit, but it's already pretty quick with the control lines. And let's go ahead and speed it up now. At a certain point, it's not even possible to tell that the thing's moving because it flickers so quickly. Good. That is full speed for my computer. There is a clock divide. I'm not sure what the minimum clock divide is because of the issue with the lowest byte, but for all intents and purposes, it's instantaneous at this point. So if we look at the serial connection in Secure CRT, you can see that I've been prompted to enter my first value for the multiplication. I'll do 3 demonstrations. The first one was pretty simple. Now I'll do a positive number times a negative number. How about 90 times negative 76? And finally 2 negative numbers. How about negative 75 times negative 4? So for all intents and purposes, the computer seems to be working. And at this point, I'm going to go in and explain how it's working and tell you a little bit about my special feature. Now that we've seen the computer, I'm going to jump right into taking a look at the instruction set. So my computer is a 16-byte word addressable computer. The addresses that are used to load and store memory are incremented by 1. So when the program counter is 0, that's the first instruction. When it's 1, that's the second instruction, etc. There are 4 different types of instructions that my computer understands. There's what I call the rfunc type, which is the normal add, and, or instructions that take 2 registers. In this case, the destination register acts as an accumulator, and the least significant byte is for a func code, which is passed through to the ALU. There is a R immediate type instruction, which is used for load and store words, where you can specify a register to use as a source or a destination, an address, and then an offset off of that address. There's an immediate type of instruction, and these are for instructions like AND immediate or immediate, add immediate. And in this case, and in all cases, the immediates are signed decimals in 2's complement notation. And then finally, there's a branch type instruction, which is an unconditional branch. These are the different instructions specifically that my computer can execute. There is the load upper immediate instruction, the add instruction, the subtract instruction. There's a shift left, a shift right, and or complement test, which sets status flags like the destination register is equal to the source register or the destination register is less than the source register. I use these for all of the conditional branch instructions. There is a shift right arithmetic instruction which does assign extended shift. There is a move register which sets the destination register to equal the source register. There's a multiply instruction. And then the typical branch and link, jump register, branch unconditional instructions. There is also a pseudo instruction that the assembler uses, and that's load immediate. This is translated into a load upper immediate and an or immediate instruction. Finally, there are 16 registers in my computer. Like MIPS, there's a 0 register and an assembly temporary register. And then there are 6 temporary registers for use by the assembly programmer, as well as 6 saved registers with a calling convention similar to what MIPS and ARM denote should be used for temporary and saved registers. Register 14 is the stack pointer, and register 15 is the return address. This register cannot be written to. So at this point, I'm going to jump ahead to the emulator, which I've set up to be almost like a primitive debugger. So I'm going to show you some of the things that I've done, and it might be a little different than what other people did, but maybe not too. So I'm going to go ahead and run it, and a prompt comes up. I tried to base it a little bit off of GDB. If you type a question mark, you can see the things that you can do. You can step forward through one instruction. You can disassemble the neighboring instructions. It's possible to dump memory, to set memory, to dump the registers, and to change the registers. So just to give you a little demonstration, I'm going to go ahead and pull up my MIF file and run until hexadecimal instruction B3. So to do that, I'm going to set a temporary breakpoint at B3, and it's prompting me for my first value, and it prompted me for the second value, but I know it's actually now at a breakpoint because the dollar sign has come back up, the prompt. So at this point, let's go ahead and take a look at the contents of the registers. And you can see here are the 16 general purpose registers, as well as my special status register, which is CPSR. The CPSR register is set by the test instruction and the test I instruction. And basically the first bit, bit 0, the least significant bit, is set to 1 if the two registers that were compared were equal, and bit 2 is set to 1 if the first register is less than the second register. So those were the registers, and let me go ahead and dump some memory. Here are the first 16 words of memory, and you can see I put in, I entered value 100 over here as my first number that I wanted to multiply with, and right at memory instruction 5, you can actually see 100 here in ASCII values, ASCII chars. That's where the memory was saved to. And just to see where we are, I'm going to print, which disassembles the 5 instructions above the current program counter, as well as the 5 instructions below it. So if I step a couple times, I can see that I've just jumped into a function with the branch and link, and you can see I'm pushing the stack and getting ready to start executing that function. Lastly, I want to talk about my special feature, which was a hardware multiplier. I decided to do a hardware multiplier because I took a look at the assembly program that I was writing, and I realized I was using multiply all over the place. I originally implemented multiply as a function, and that function had about 20 to 30 instructions. That meant that every time I multiplied one number, which I might do dozens of times, I was loading memory 30 times and then executing a bunch of other instructions, which turned out to be very costly. So I decided to implement this hardware multiplier to speed that up, and I did that using a Wallace tree architecture. To review quickly, I want to give an example of what multiplication might be in binary in sort of the way that I was doing it before in a function. And let's say I want to multiply 4 by 2, and this is how it would look in binary. And the way that we did it in class and went over it is that we would take each bit in the multiplier, and if it was a 0, we'd basically carry down the multiplicand, and then for each bit of the multiplier, shift the multiplicand 1 bit to the left, and if it's a 1, propagate it down. That means that in this 4-bit multiplier, I have 4 partial product sums before I'm able to get my answer. What I did instead was took that idea, and there was a paper written in 1965 by a guy named Wallace, which laid out an idea for his Wallace tree. And this idea was that rather than doing a sequential multiplier, let's do a multiplier that takes a constant amount of time. And it's able to do this by using rather than regular adders, it uses these carry save adders, which have 3 inputs, sort of like a full adder, and then 2 outputs, also like a full adder, but the outputs are used differently. The carry output and the sum output are of the 3 numbers, not just 2 numbers for the full adder. So you can see you can make this Wallace tree, and I used 15 carry save adders, and then you finish it up with a regular full adder, and I'm able to multiply now in one cycle rather than probably the thousands that it was taking before. And yeah, that's my presentation. So thanks for your attention. I hope you enjoyed it, and I'm around if you have any questions.